If you've been writing code for any length of time, you know the dream,
Yeah.
right? An AI that doesn't just autocomplete your if statement, but actually builds the entire feature.
Tests it and commits the code for you.
Exactly. We are diving into a moment where that fantasy is, well, rapidly becoming the standard workflow. We're moving beyond the Copilot era and into the age of the autonomous software development agent.
It's a huge leap.
Today, we are dissecting a new operational philosophy for this human AI software creation, and it's called vibe coding. Our mission is to really understand the new rules of engagement. You know, what the core architecture looks like, how developers choose their collaboration style from 5 distinct models, and crucially, what fundamental security trade-offs emerge when you automate the core act of programming.
And this is more than just an iteration on existing tools. It's a paradigm shift in capability.
Oh.
Well, think back to the early LLMs. They were great at suggestions, but they were purely supplementary. You had to manually copy-paste, debug, review every single line. They were just, very sophisticated editors.
Right. A fancy autocomplete.
But now, with these advanced models like GPT-4 and the latest Claude iterations, we have true coding agents, and the difference is autonomy.
Okay, autonomy. What does that mean in practice?
It means they don't just output text. They interact with the entire programming environment. They can run shell commands, they can execute your test suites, read the error logs, and, this is the key part, they can self-correct.
And the performance jump is just staggering. I mean, some of the sources show examples like OpenHand solving over 53% of the tasks on the SW Bench verified benchmark.
Which is incredibly complex.
That's not a helpful suggestion. That's a working solution, delivered autonomously.
Exactly. They're now capable of self-learning and complex problem-solving right inside the environment. But, 53% is not 100%. They still need human guidance.
And that's where vibe coding comes in.
That's why we need it. It's the formal structure for managing this new, powerful, but still imperfect autonomy.
Okay, let's unpack this. If an autonomous agent is writing the code, the human's job changes completely. The sources define this relationship as a triadic collaboration. Forget the Greek letters and the academic notation for a second. What are the 3 key players here, and what do they do?
So the 3 elements are the human, the project, and the agent itself. And the reason it's formalized is because the relationship is no longer just human tells agent what to do. It's much more dynamic.
Okay.
The first element is the human developer. You're the high-level manager now. Your job shifts to 2 critical functions. Requirement cognition.
Which is basically translating a messy business need into precise instructions.
Precisely. And the second is quality discrimination. That's judging the output not just for functionality, but for architectural fitness, for safety. You set the vision and you set the boundaries.
And the second player is the software project. This isn't just the files on the disk, is it? It's the whole environment that imposes constraints.
That's right. The project provides this deep, 3-dimensional context space. That includes the existing codebase, the schema of your databases and APIs, and critically, all the domain knowledge, your internal docs, design patterns, company standards.
So the project context dictates where the solution has to live.
It ensures the agent doesn't build a beautiful solution that simply doesn't fit your existing tech stack.
Okay, so that's the human of the project. What about the third element, the agent itself?
The coding agent takes your instructions and the project's context, and it dynamically orchestrates its tools and its memory to generate the code. The magic here is the dynamic context assembly. It's not just reading a static file.
It's doing more.
Oh, yeah. It's performing REG, checking the shell, accessing its own memory of previous attempts all at the same time just to generate the very next token of code.
So if we connect this to the bigger picture, why do we need this formalism now? I mean, why not just call it enhanced Copilot?
Because vibe coding solves scaling problems that basic copilots couldn't even touch. Historically, if you wanted a full-stack application, you needed a team, right? Front-end, back-end, database engineers, DevOps.
A whole crew of specialists?
Vibe coding offers team-scale capabilities to the individual. A developer can focus entirely on defining the requirements for a feature, and the agent just implements it across the full stack.
That radically reduces the learning overhead for one person.
You don't need to master Kubernetes and React and PostgreSQL. You need to master prompting and oversight.
That's a huge shift in talent demands. It effectively turns a single developer into an orchestration layer.
And that leads to the second major benefit, democratization.
Meaning?
When natural language becomes the primary creation interface, you broaden the ecosystem beyond career programmers. Think about a medical researcher who desperately needs a specific data analysis dashboard built.
They don't have time to learn a new coding language.
Exactly. They don't need a computer science degree. They just need to articulate their domain needs clearly and then evaluate the resulting code critically. They can become software creators.
Okay, this is where it gets really interesting for me. This isn't a one-and-done instruction. The core mechanism of vibe coding isn't about throwing requirements over the fence. It's an interactive continuous loop. It's modeled academically as a constrained Markov decision process, which sounds terrifyingly complex. What does that mean for the person sitting at the keyboard?
It means you hold the steering wheel, and the agent is driving a very, very fast autonomous vehicle. Every iteration is a step in a process where the human applies constraints to guide the agent toward an acceptable solution.
So the agent spits out some code.
It generates an output, a chunk of code, a test passing, a file change. You, the human, evaluate it. If it meets your quality standards, you accept it. If it doesn't, you send a precise correction signal back.
And that signal isn't just try again.
No. It might be use the existing database helper function, or this logic exposes a security risk. It's specific.
So that human guidance through continuous feedback is the core mechanism. And the research highlights something called iterative task expansion. It flies in the face of decades of software doctrine.
Absolutely. Traditional development, like waterfall, demanded that requirements be exhaustively planned and frozen early on.
Right. Get the sign-off before you write a line of code.
Vibe coding embraces the reality that requirements are messy and incomplete. They aren't frozen, they crystallize through interaction.
We've all been there, haven't we? The client asks for feature X, the agent builds it, and then you look at the output and realize, oh, I forgot to specify that it must handle authentication using our custom oath flow.
Exactly. The agent's output exposes the implicit requirement you missed. This is progressive clarification. You don't need to exhaustively plan upfront. You can immediately supplement the constraints for the next iteration.
That's what they call dynamic constraint reinforcement.
And that's how the system moves from a vague idea to a precise, architecturally sound piece of software.
So if we step back and look at the whole system, humans define the evolving problem and the why, judging if it's right. The project defines the where, the architectural boundaries, and the agent manages the complex how, the implementation.
That's the triadic relationship.
This radically changes a developer's workflow, though.
Yeah.
You can't just use one rigid process. You have to choose your collaboration style.
Precisely. The research breaks down 5 core development models. These models define the balance of trust, speed, and constraint. You choose the right vibe for the task at hand.
And they're based on what?
What's fascinating is that they're defined along 3 axes. How much human quality control is needed, how structured the constraints are, and how much context is being managed, and you can mix and match them.
Okay, let's walk through them, starting with, I guess, the fastest and riskiest one.
That would be the unconstrained automation model, or UAM. This is pure velocity. You provide a prompt and you trust the agent completely with minimal or zero human code scrutiny.
It sounds a lot like rapid application development, RAD, speed is king.
It's the closest analogy. UAM is really only suitable for disposable prototypes, internal scripts, or proofs of concept where technical debt and security risks are just acceptable. You're trading long-term stability for immediate delivery.
Okay, that's the high-risk, high-reward model. The polar opposite of that seems to be the iterative conversational collaboration model, or ICCM. This sounds like an AI version of pair programming.
It is, really. ICCM positions the agent as the tireless, rapid driver generating code almost instantly.
And the human developer is the discerning navigator.
Exactly. The human reviews every single output, providing continuous granular feedback. This model maintains high velocity. The agent never stops writing code while ensuring high quality. But
There's catch.
it requires a very experienced developer. If you don't have the discernment to quickly identify a subtle flaw in complex agent-generated logic, this model just breaks down.
So ICCM is high quality, high velocity, but only if the developer is senior enough to keep up. Okay, next up is the planning-driven model, PDM.
PDM is for the architecture purists. It brings structure back into the process. The humans establish clear, detailed plans, defining module decomposition, class structure, API contracts, before the agent writes a single line of functional code.
So it's like the upfront design phase of Waterfall.
Very much so. The agent is then strictly constrained to implement within those predefined architectural boundaries. The benefit here is superior modularity and architectural coherence. It's essential for large-scale, long-lived enterprise applications.
And the fourth model, the test-driven model, TDM, that one replaces human scrutiny with machine certainty, right?
Precisely. TDM inherits the philosophy of test-driven development. Humans write the acceptance tests that define the desired behavior, and the agent's whole objective is simply to generate code that satisfies those tests.
The test failure messages become the correction signals.
They're perfect, objective correction signals for the agent. Now, if the agent writes insecure code that passes the test, the human still needs oversight. But for functional correctness and avoiding regressions, TDM provides objective verification. It changes the interaction from, does this look right, to, does this work according to the contract?
Okay, and finally, the fifth model, the context-enhanced model, CEM, is the one you can sort of layer onto everything else.
CEM is critical for large projects. Its goal is to ground the AI in reality. It uses advanced techniques like retrieval augmented generation, or ARGI, and code-based vector indexing.
ARGI is a term that gets thrown around a lot. For our listener, how does ARGI specifically change the way the AI codes?
Think of ARG as giving the agent the world's most detailed, project-specific memory. When the agent needs to write a function, instead of relying solely on its vast general training data.
It looks at your local stuff first.
Right. The RH system retrieves semantically relevant snippets of your existing code, your internal convention, or your architectural notes. This means if you have a custom logging utility or a specific way to handle database connection pooling, the agent knows to use it.
Because the relevant context was retrieved and fed into its prompt.
It ensures consistency and adherence, which is vital on a code base spanning millions of lines. You'd often pair CEM with PDM for the highest quality projects.
This all raises a really important question, though. If we're orchestrators, not authors, and we're prioritizing the speed of the agent's implementation to what happens to security, we're relying on high-level approval, not line-by-line debugging. The core trade-off of vibe coding has to be speed versus certainty, doesn't it?
It absolutely is the critical trade-off. Because the agent is writing thousands of lines of code based on high-level prompts, a developer might approve implementations that contain subtle but highly critical flaws. The research confirms that LLMs often reproduce vulnerabilities found in their training data.
And manual review just can't scale to that complexity.
It can't.
So what are the biggest specific risks of relying on these autonomous agents that we need to be prepared for right now?
The first major risk is what's called cascading errors. In an autonomous environment, you often have multiple agents working on different components that interact with each other. If Agent A generates a flawed component, say, an insecure API interface, that output is then consumed as input by Agent B and Agent C.
So a small mistake gets amplified.
It turns a small, local inaccuracy into a systemic failure that propagates across the entire software architecture. That could lead to widespread security vulnerabilities or data leaks that are incredibly hard to trace back to the original mistake.
And given the pace of these agents, I can imagine dependency management just becoming a complete nightmare.
That leads directly to the second risk, dependency proliferation. Autonomous agents, when they're tasked with solving a problem quickly, tend to introduce new libraries and packages without any human oversight.
And sometimes they just make them up.
Sometimes they hallucinate packages, or they choose deprecated or vulnerable modules because they happen to be the most statistically common answer in their training data. This uncontrolled expansion of third-party libraries just puzzle. It inflates the software's attack surface dramatically.
You're trading quick development for a massive governance and security compliance headache down the line.
A huge one. And the third risk sounds like a failure of intention. Alignment failures.
What do you mean by that?
This is perhaps the most insidious one. Agents are fundamentally optimizing for textual success. They want to pass the prompt and satisfy the immediate constraints you gave them, but they might completely disregard crucial implicit constraints like security, maintainability, or efficiency.
So it works, but it's not good.
The agent might deliver functionally correct code that is deeply unsafe. Maybe it leaves sensitive data unencrypted or implements business logic that is technically correct but violates an organizational policy. It passes the functional test, but it fails the vibe check of safety and corporate standards.
So if human eyes can't scale to review this volume of complex code, the solution has to be automated security. How do we shift from the old model of, delayed periodic scanning to what the sources call scalable oversight architectures?
We have to integrate real-time automated analysis directly into the core prompt generate validate loop. Security assurance can no longer be a separate stage you run in CI/CD once a day. It has to be intrinsic to the generation itself.
Can you give us a concrete example of what that integrated analysis looks like in the agent's workflow?
The best example is in-flight SAS scanning. So imagine the LLM starts streaming its generated code into the developer's environment. Before the code is even fully completed, a real-time static analysis tool should be analyzing that incomplete code on the fly, flagging potential vulnerabilities.
Like SQL injection flaws or buffer overflows.
Exactly. And crucially, this information isn't just displayed to the human. The oversight system feeds that vulnerability flag directly back to the LLM.
So the agent sees its own mistake.
And it recognizes the violation and self-corrects its output before the developer ever even sees the flawed version. This transforms security from passive auditing into active, preventative modification.
That's powerful. It turns security from a blocker into a self-correction mechanism. What about testing the actual runtime behavior, the dynamic side of things?
That's where sandbox dynamic analysis comes in. When the developer hits run to test the new functionality the agent created, the execution happens inside a fully instrumented, isolated sandbox.
And this sandbox is doing what?
It's performing just-in-time JAS dynamic application security testing and fuzzing on the new functions. It checks for runtime errors, memory leaks, or insecure network communications, providing immediate feedback on the code's dynamic behavior and potential exploitability.
So this rapid cycle ensures that even functionally correct code that behaves badly gets caught.
It's immediately caught and fed back to the agent for refinement.
So the developer's role isn't eliminated then, but it's elevated.
Mm-hmm.
They become the interpreter of all this automated feedback.
Absolutely. The human developer becomes the final arbiter. Their mastery shifts from writing boilerplate to interpreting highly detailed automated security and quality feedback. They're responsible for making the final risk-based decision about accepting the agent's work, even when the system provides conflicting signals.
It's a fundamental move from code author to system manager.
That's it. Exactly.
We've taken a fascinating journey today, outlining the architecture of vibe coding, from the necessary constraints provided by the human in the project, through the 5 key models that define collaboration, and finally to that critical trade-off of speed versus security.
The core transformation is clear, I think. The future developer's expertise lies in context engineering. Their mental energy has to shift away from syntax and logic mastery toward curating perfect prompts, providing structured constraints through planning or tests, and prioritizing automated quality supervision.
They're orchestrators of highly complex, multi-layered systems.
That's what they are.
And this leaves us with a provocative final thought for you to consider. If future coding agents continue to increase their capabilities, potentially generating code so vast and complex it surpasses the comprehension of any single human developer, can our governance and oversight systems, even those using AI debate and recursive supervision, scale fast enough to keep them reliably aligned with human intent? Is the future of software management simply a race between AI capability and AI governance?